All right, hi everyone. Thank you for having me here today. So my research talk is evolutionary dynamics on any population structure. We'll discuss what this means. This graphic was made by my collaborator, Babak Fatui. And it's not just pretty, but it actually captures some of our results. These different graphs we see here have different effects on the evolution of cooperation. And we'll get to what that means. Okay, so what I want to do is talk about the big question of population structure and evolution, introduce a particular model of evolutionary games on graphs, talk a little bit about the method, since I understand this is somewhat of a mathematical audience, and then talk about the results in terms of conditions for cooperation, examples of different population structures, some numerical experiments, and extensions. So the big question that I've been interested in since I've come into this field is how does the structure of a population influence its evolution? And structure can mean a lot of different things. Population can be structured into groups. It can be structured in terms of a spatial habitat. There can be some kind of network of interactions in the population. There can be some kind of social assortment where individuals interact in a non-random or non-uniform way with others. All these are various types of population structure, and you can think of these, from microbes, bacteria, all the way up to humans. So this is my big question. And then a major sub-question of that is, how does the structure of a population influence the evolution of social behavior? What do I mean by social behavior? What I mean is behavior that affects others. So this is an example of what I would call social behavior, even though it's maybe not what colloquially most people would call it. This is a growing population of Pseudomonas aeruginosa, and some of them are producing a chemical called pyoveridin, which scavenges iron from the environment. The interesting thing about that chemical is that it diffuses through the environment. So the producer doesn't necessarily reap the rewards of producing it. It goes throughout the environment and kind of helps all the other cells in the neighborhood. The other interesting thing about it is that it's fluorescent, so we can see which cells are producing it at any given time. And we can kind of understand this as a social dilemma. In that it's costly to the individual cell to produce pyoveridin, and the benefits go, for the most part, to other cells. So we have to ask, what drives the evolution of this behavior? Why does it evolve when it might be overall costly to the individual producer? So part of the big question is, can population structure help address this question? Can population structure help resolve these kinds of social dilemmas? Okay, so I'm a mathematician. I don't actually do those microbial experiments, but I like to represent things abstractly. And the way that these are represented is an evolutionary game theory. So it's an approach to studying how social behaviors evolve, where we model interactions as a matrix game. So here's a simple pairwise matrix game. We have two individuals interacting. They can be of type A or type B. And there's 4 different possible payoffs. When I write a matrix like this, these payoffs are to the row player. So that means, for example, if an A interacts with an A, they get payoff little a. If an A interacts with a B, then the A player gets payoff little b. To find the payoff to the B player, we look at this column here. A B interacting with an A would get payoff little c, and a B with B would get little d. So that's how we read that kind of matrix. This is just regular game theory, but we want to tie it into evolution. The way we do it is to say that somehow the payoffs in this game should affect reproductive success. So the strategies that do well in this game should reproduce more, and then therefore the strategies spread. Of course, that then leads to a different population state, and maybe that changes which strategies do well. So there's a feedback there. in particular, one of the biggest questions is to look at the evolution of cooperation. And so in that case, we can look at a kind of stylized version of the prisoner's dilemma, where we have cooperators, defectors. Cooperators pay a cost C, some cost, and that gives a benefit B to whoever they're interacting with. So this is just a pairwise kind of cooperative interaction. Defectors don't pay any costs and don't give anyone any benefits. So that leads to this matrix right here. If B and C are both positive and B is larger than C, then this is a prisoner's dilemma. So in that case, it's always better to defect no matter what the other player does, right? Because cooperating can only incur a cost to yourself. So defection is a dominant strategy in that case, and leads to a prisoner's dilemma. If there's another interesting case is if B is negative. In that case, this no longer represents cooperation, but it can represent a spiteful behavior. What we call spite is when an individual pays a cost to harm another individual, which is something we also see in biological populations and human populations as well. So these are two different scenarios that this matrix could represent. Okay, so we're interested in the effects of spatial structure and how spatial structure affects the evolution of behaviors in this game. So how do we model spatial structure? I'm going to present a model where whatever population structure there is represented as a weighted graph. The vertices here represent individuals, and the edge weights represent frequency of interaction and replacement. So, for example, these two vertices will interact with each other more frequently than these two. You'll notice that the vertices are drawn with different sizes. That reflects something called the weighted degree. It's the total edge weight adjacent to that vertex that ends up being an important quantity.
What do you mean by replacement?
We'll get to that. Okay, so in a given population state, we have individuals that can be of types A or B, and they're going to interact with each other. Their interactions are described by a 2x2 matrix game, as we said before. And every individual retains a certain payoff after game interaction. That's going to be the edge-weighted average of the payoffs they get from each neighbors. So here's some examples. Take this A over here. It interacts with this other A, and it receives payoff little a with a weighting of 3, right? Because there's an edge weight of 3 there. This A interacts with two B individuals, getting payoff little b. That has a total edge weight of 5, right? So overall, A retains the average of those, so that's 3A plus 5B over A. Make sense? All right. So that quantity describes how well these individuals are doing in this game. Now we need to translate these payoffs into reproduction somehow, and that's going to be the next couple of slides. So first of all, we're going to translate the game payoff into a reproductive rate. And that's going to be given by, so if little fi is the payoff from the game, the reproductive rate, big Fi, is going to be a baseline rate of 1 plus some amount that is determined by the game. And that's scaled by a parameter delta, which we'll say represents the strength of selection. So in terms of finding analytical results, we will kind of be limited to the regime of weak selection, delta much less than 1. That means that the game has only a small effect on reproductive success, right? So it could mean there's a lot of different things going on in this population. One of them is this game. It has some effect on reproduction, but it's a mild effect overall, considering everything else that's happening.
Is there something qualitative that you're thinking about when you say weak selection?
So it means that, well, it means that the, overall this one game interaction, represents a small portion of what, what goes into their reproductive rate. You could also say, mathematically, it's going to mean that we can look at kind of a process of neutral drift, and then look at weak selection as a perturbation of that neutral drift process. Yes?
How general is the assumption of weak selection in reality?
Well, you have to, so, mutations in biological populations, like realistic levels are like 5% would be a pretty strong effect of a mutation, maybe more like 2 or 3% for a, more realistic assumption, to the extent that these have been measured in microbial populations. So those are pretty small. What we need to do to kind of figure out, how small is to compare these weak selection results, which are kind of limiting results, with simulations. And we've done that. So we've done simulations for 2.5% selection strength, and all the results we present here are pretty good, going up to that selection strength. So we think it's reasonable. It depends, of course, on what trait you're looking at. So if a trait is really like a life or death trait, then you wouldn't want to think about weak selection. Yes?
So if one of A or B is benefit from the cooperation or something and it has higher reproductive rate, and then will that back to affect the weights of each edge?
We're going to view the graph structure as static in this model.
Okay.
So that's, it's certainly very interesting to look at dynamic graph models, but we're not there yet. Yes?
Why do you use the average of the edges?
We also have analyzed the case that it's the sum. That's just as analytically tractable. The average is a little bit more elegant because it doesn't give so much of an intrinsic advantage to those that have higher edge weights. But it depends on the trait you're looking at. So maybe, maybe you'd want to give this one an average kind of intrinsic advantage from having so many neighbors. So we can analyze both cases. Yeah?
I guess in certain cases, the graph could be assumed to be regular, in which case the average would just be the same as the sum.
That's true, but we actually want to go beyond regular graphs here. Yeah. So how does reproduction happen? So we're going to use an update rule called death-birth updating. We also studied another one, but we'll focus on death-birth updating. So in death-birth updating, so everyone has a payoff. Everyone has a given reproductive rate from that payoff. And then the way the update works is we first select an individual to be replaced. And that's going to be made uniformly at random. So let's say it's that former B right there. So that's now a vacant spot. And someone is going to reproduce to fill that spot. We're assuming this is a haploid asexual population, so only one individual gets to reproduce. That's going to be a neighbor of that vacant spot, and the choice of which neighbor is going to be proportional to reproductive rate times the edge weight to the vacant spot. So if you have a higher payoff, you have more chance to reproduce, but also if you're closer to this vacant spot, then you have more chance to reproduce. So it takes both of those into account. And that was the remark about the edge weights, affecting frequency of reproduction. So let's say that A is chosen to reproduce, then it fills the vacancy. And for the moment, we're going to assume there's no mutation. So the offspring inherit the type of the parent. That's, again, an assumption that we can relax and without too much trouble, but we'll assume it for now. Okay, so that's the basic model. This leads to a new population state, then everyone interacts again, then there's another update, etc. So eventually, as we iterate this over and over, one of these two types will become fixed in the population. Right? There's two absorbing states. There's the state of all A or all B. And we're interested in the relative probabilities of those. Specifically, we're going to look at the fixation probability, rho A, defined as the probability that type A becomes fixed, starting from a single A at a single vertex, chosen uniformly at random. So we kind of throw a new type somewhere onto this graph, let evolution happen, and eventually either A will take over or B will take over. We will call rho A the probability that A takes over. And then kind of conversely, the fixation probability of B is defined as we start with an all A population, throw one B in there somewhere, and look at the probability that B takes over. Right? So these are both biologically relevant because new types usually come in one at a time, right? Either through mutation or through migration from somewhere else, and then they either become fixed or they disappear. Yes?
You're averaging over all the nodes for the initial mutation, for the initial type.
Yes.
Uniform distribution of?
Yes, that's right. And we're going to say that type A is favored if the fixation probability of A is greater than the fixation probability of B. This also ends up being equivalent to the statement that if you average over a long period of time with a small amount of mutation between the types, then overall you're more likely to see A's more often than B's. Okay, so...
Are you talking about a mutation selection balance?
Exactly, yes. Yes, so that means that A would be favored in the mutation selection balance under rare mutation.
Okay.
Yes, got to use the right language. All right. Okay, so we've discussed the model, and this is our main quantity of interest. This is a generalization of a model that's quite well studied. So the first major result on this question was for a large, unweighted, regular graph. In that case, it was found that cooperation is favored in the donation game if and only if this very elegant condition is fulfilled. B over C greater than K. That means, so the benefit-cost ratio should be greater than the degree of each vertex. So if you're on a graph of degree 4, then you should have a 4-fold benefit relative to the cost of cooperation in order for cooperation to succeed. So this is the condition for a large, unweighted, regular graph. This was generalized for unweighted, regular graph of any size. So there's a little correction here. It's n minus 2 over n over k minus 2. You can see as n gets large, this just becomes k. Okay. Okay. Maybe I touched something somewhere. All right. We'll see. Hopefully it won't happen again. But both of these results are for regular graphs. And that's a pretty strong assumption, right? So in real-world networks, they're very often not just heterogeneous, but strongly heterogeneous, right? We very often find these hubs that are very well connected.
Ben, you have a question?
Yeah.
Going back to the previous slide.
Yeah.
Can you define again what it means for cooperation to be favored?
Cooperation is favored if the fixation probability of cooperators is greater than the fixation probability of defectors.
Okay.
Or if cooperation is favored in the mutation selection balance for small mutation.
So these are A's and B's that have a fixed strategy, always cooperate or always defect?
Yeah, so in this case, the A is always cooperate and the B is always defect. That's right. There's an obvious question of how to generalize these results to non-regular graphs, but the mathematical theory was fairly limited. There was a few toy examples that were well analyzed, such as the star graph. There were also many computer simulations, some kind of approximate approaches, but no analytical theory. There was a interesting paper from 2015 that shows that if you go away from weak selection, so if you go to strong selection of some sort, then determining whether a given strategy is favored on an arbitrary graph is an NP-hard problem. So that's a real limit on how much we can do for these kinds of models without assuming weak selection. But we're going to assume weak selection and derive a condition that applies to any weighted, undirected graph.
How small does delta actually have to be, and what happens in the math? And you can punt on this, but like it seems like there's a qualitative difference when that delta crosses some threshold. So what's actually?
So the most strict thing that's needed is n times delta much less than 1. But actually, it's been shown that the results can be extended, a good deal beyond that regime. At least it's been shown that through simulations. But I think strictly delta needs to be less than 1 over n, which is a quite strong condition in terms of weak selection. All right. So I'm going to talk a little bit about mathematical methods of how we obtain this solution. An important quantity here is the weighted degree of a vertex, which, as I mentioned, is the sum of adjacent edge weights. And then we want to obtain something called the relative weighted degree. So we divide the weighted degree by the sum of all weighted degrees. So this then becomes a probability distribution. It's a very important one. It turns out to be the stationary probability of the vertices under random walks on the graph. And we'll see random walk theory come up in this in our methods. It also turns out to be equal to the fixation probability of a neutral mutation arising at a vertex. Right? So a neutral mutation arising here has 9 over 2 times the fixation probability of one arising here. And we can also understand this relative weighted degree as the reproductive value of a vertex. So it's kind of more important to capture one of these high degree vertices in terms of sweeping to fixation. Okay, so the method we're going to employ is perturbation of a Martingale. As I said earlier, it's perturbation of the neutral drift process. So to define this, let's just define an indicator variable for each vertex. So it's 0 for type A, and that's backwards. It's 1 for type A and 0 for type B. Sorry, that's a typo. 1 for A, 0 for B. And then we're going to find the degree weighted frequency as this weighted sum where these indicators saying that I is occupied by an A are weighted by the relative weighted degree. So this is a number between 0 and 1 for every population state. It's 1 if the A's have taken over. It's 0 if the B's have taken over. And I claim that it's a Martingale for neutral drift. So that's why this is an important quantity. That means that in any state, its expected change is 0. Right? So if you're start in any given state, it might go up, it might go down, but it's on expectation, it will stay the same. And then we're going to study weak selection as a perturbation of this Martingale. So we're going to use the fact that this has expected change 0 for neutral drift and say, what if we introduce a little bit of selection? How does that change things? Okay, so to define a few more things, we're going to say let d of s be the expected rate of change in this degree-weighted frequency from a given state, right? So if we introduce selection, then it might go up or down. And we'll do a Taylor expansion. So the important point here is that the 0th order term, when delta equals 0, that's neutral drift. And so when delta equals 0, the expected change is 0. So we have no 0th order term here. We have a first order term that describes weak selection. So this is like how the degree-rated frequency changes from a given state under weak selection. And then we have higher order terms, of course. But for weak selection, we're going to focus on this term. And there's this result that we used that the fixation probability of type A is equal to 1 over n, which is the expected value for neutral drift, right? Under neutral drift, kind of everyone has an equal chance to spread their genes through the population. Plus delta times some expectation of this first order term. And that expectation is taken over the process of neutral drift, plus higher order stuff. So the idea of this result is that we can look at the distribution of states that arise under neutral drift. And that has a technical definition, which I won't go into. But we can look at that distribution of states and evaluate this first order expected rate of change from all of those states. And then take that expectation, and that will tell us ultimately what the fixation probability is to first order and selection strength. That's the scheme here.
Is it the stationary distribution under neutral drift that you perturb off of then?
That's one approach, but that's not actually the approach that we used. We didn't use stationary distributions. We used, because for the stationary distribution, you need to have recurring mutation.
Yeah.
So with this method, you start from one new mutant, and you just let the process run. And so you just look at the expectation of different states from that given starting state. Yes?
In those higher order terms, is there any scaling in n present, or is it only a delta squared?
Probably there's scaling in n. But yeah, I don't think I could say all the details offhand about that. There's in this Chen 2013 paper, there's technical conditions on what exactly this error term is. I mean, this holds for a fixed value of n. That much I can definitely say. So we now need to understand this d prime quantity. We've kind of reduced it to understanding how this d prime behaves under this particular expectation. For that, we need to understand something about what is this distribution of states that arise under neutral drift. And in particular, what's the pattern of assortment, right? So how likely it is, for example, for an A to be next to another A. And then the method we're going to apply here is coalescing random walks. The idea is that we start from two given vertices, and we trace their ancestries back in time. So at some time, we kind of model their ancestries as random walks. So say this individual had a parent there, this individual had a parent there. At some past time, their ancestries converge into a common ancestor, right? So if we model these as random walks, then there's a certain coalescence time, which is the expected time, should say expected there. It's the expected time for two independent random walks from I and j to meet. That's going to represent the time to the most recent common ancestor of those two sites. It turns out to also be equal to the time that I and j spend as different types in the evolutionary process. Right? Eventually, they'll converge to the same type, but for some amount of time, they may be different, and the expected amount of time that they're different is equal to their expected coalescence Another way of saying that is if t is the total expected time to absorption, either fixation of A's or fixation of B's, then t minus tau ij is the expected time that I and j spend as the same type, right? Just by subtraction. Yes?
Why is the time equal? If they are the same type, you can still have a very long time until they really coalesce.
Yes,
so
sure.
why is it equal to the time that they spend as different types? Even if they're the same type, they can have a very long time until the more system come another structure.
It's equal in expectation. So, this is, I'm referring to this average over the process of neutral drift.
But after coalescence, they're definitely different. I was wondering the same thing. Sorry, after coalescing, they're definitely the same.
Right.
But before that, they might be the same.
Yes, that's true.
Maybe if you know that they started as different.
Yeah, maybe.
No, I don't think that's it. Yeah. No, I know that this is a true statement because we proved it, but I'm having trouble addressing that particular question.
Am I supposed to imagine the scenario where we start with, say, all B, we seed it with one A, we wait for a while. Eventually there are maybe many A's, and I want to know how far back for two given A's before they, sort of reach their common ancestor, or should I be thinking about an A and a B and going back?
So this is the coalescence time is just defined for the graph structure. So it's just saying you don't need to think about A and B's for the coalescence time.
Okay.
It's just saying you pick two vertices on the graph, have them do random walks, and calculate the expected time until those random walks meet.
And these random walks are weighted by edge weights? Like
yes.
The probability I move to a neighbor is proportional to the edge weight?
Right, that's correct. Yeah. Okay. Right, all right. I'll think about that question as I'm talking. So the coalescence times satisfy this fairly straightforward system of equations. It says that if you start at the same vertex, the expected coalescence time is 0. If you start at different vertices, then the intuition of, we have a recurrence relation here where it's like you spend time 1, and then one of the two of them takes a step. And if I steps to k, then your coalescence time is now tau jk. And if j steps to k, then your coalescence time is now tau ik. So this is just a kind of straightforward recurrence relation. And these coalescence times, the important relationship that we need is one between coalescence times and kind of assortment. And that's given by this this equation here, where this is, again, an expectation over states under neutral drift. And SISJ is equal to 1 if I and j are both type A, and is 0 otherwise. And so this quantity on its own would have infinite expectation, but if we do 1 over n minus that, then it has a finite expectation which is proportional to the expected coalescence time.
What's S? S is the indicator of...
S is the indicator, yeah, so of A, that's right.
Infinite expectation?
Finite graph, right?
Right, because there's a non-zero probability that A will become fixed. And in that case, SISJ equals 1 for all time.
What's the expectation over?
Expectation is over the process of you seed a random individual and you let neutral drift run forever.
Forever. But it still wouldn't be infinite. It's a finite quantity. You're taking expectation of something.
oh, we're integrating over time. Maybe that's the issue here. We're taking we're taking an integral. So that yeah, these brackets here indicate an integral from time 0 to time infinity.
Okay.
So that's how you get infinity out of that. Okay. Right. Maybe that addresses the other question as well to some extent. Okay.
Can you say a little more about the intuition of that formula? Now that we know it's an integral.
So the important thing is that tau ij is negatively related to the probability that, or to the frequency that I and j have the same type. So if they have large coalescence time, then they spend less time as the same thing. Or if they have small coalescence time, they spend more time as the same thing. So the smaller the coalescence time, the more frequently they have the same strategy. The 1 over n is the fixation probability of type A. Right. So this is. So for example, if I equals j, then this is 0 here, and then this becomes 1 over n minus the fixation probability of A, which is also 0. Okay. All right. One other bit of notation. So we're interested in all the coalescence times, but the most important quantities are the expected coalescence times from two ends of a random walk. So the process here is that we're going to first choose a vertex proportionally to its weighted degree. Then we'll take an n-step random walk. So now we have 2 vertices. And then we'll compute the coalescence time from those 2 vertices. Right? So that quantity, expected coalescence time from the 2 ends of this random walk, is called Tn. And we can kind of, well, colloquially think of it as the coalescence time of n-step neighbors. That can be a little bit misleading, though, because these 2 ends of the walk might actually be the same vertex, right? So your 2-step neighbor might be yourself if you take a step and then come back. So relating to our previous results, we can say T minus Tn, where this is the expected time to absorption. So T minus Tn we'll call the expected time that n-step neighbors have the same strategy. All right. So those were the methods. So our main result, so kind of combining that Martingale perturbation formula with the coalescent theory stuff, we arrive at this result. This is for the donation game. So this is for the version where cooperators pay cost C to give benefit B. You can see this is the same formula before, but now we've computed this middle term here. That d prime term comes out to minus c times t2 plus b times t3 minus t1. Where again, these t's are coalescence times from n-step random walk neighbors. So I'll explain on the next slide what the intuition is behind this term. But we can say that cooperation is favored under weak selection if that term is positive. Right, so this is a rather simple condition expressed in terms of these coalescence times. And then this also, from this we can define a critical benefit cost threshold just by getting the B and C on the same side. So we'll call it BC star is equal to T2 over T3 minus T1, so this over that. This quantity will determine the extent to which a given graph favors cooperation. That'll be kind of a key quantity for us. Okay, so let's try to understand this condition here. Why does this tell us when cooperation is favored?
Can you say again what T1, T2, T3 are? You're going to?
Yes, but they are expected coalescence times from n-step random walk neighbors. So like T1 is the expected coalescence time from two neighbors, basically. And then T2 is like the expected coalescence time from two-step neighbors.
So the n is the 1, 2, and 3 here. That's it.
Yes, right.
Oh, that is nice.
Okay, so to understand this condition, we can take this and write it in a slightly more complicated way. So what I've done here is I've put the 2 and 3 on this side, put the 1 on this side, and I've added t to each term. These t's all cancel out, you'll notice, but we'll leave them in for the sake of intuition. I've also put in a t0 here. That's the expected coalescence time from zero-step neighbors, which is automatically 0. But again, this will help us understand what's going on. Okay, so this is another way of writing the same condition. What this condition says is that if we want to understand whether a given cooperator is favored, or whether cooperation overall is favored, we'll kind of look at a focal individual. And if that focal individual is a cooperator, it will pay cost C for itself. And that's paid for the entire time t, because t0 is 0. So it'll always pay the cost. It will gain a benefit for as long as its one-step neighbors are cooperators, right? So this is like the amount of time that its one-step neighbors spend as cooperators. So that benefit accrues over time. So the left-hand side here can be thought of as the overall accruing payoff to a cooperator, any focal cooperator that we choose to examine. The other side is going to be the accruing payoff to the cooperator's two-step neighbors. Why two-step neighbors? Well, if we could think about a cooperator here, if a vacancy opens up next to the cooperator, then it's really competing with its two-step neighbors for the opportunity to reproduce into that vacancy. Yes?
Here is C represents A and D represents B.
Yes, that's right. Yeah. So there's a real competition at distance 2 that's induced by the update rule that we chose. And so what's the payoff to the two-step neighbors? Well, the two-step neighbors pay cost C for as long as they are cooperators, and they gain benefit B for as long as their neighbors are cooperators, and their neighbors are 3 steps from the original cooperator.
Or 1.
Well, you know, 1 is a special case of 3.
That's true.
Yeah, right? I mean, it's, you know, by 3 steps, I mean 3 steps in a random walk, which may end up being like actually distance 1.
Right.
Yeah. Okay, any other questions about this condition? So we now have this quantity, the critical benefit cost threshold. It turns out this can be positive, negative, or undefined. If T3 is greater than T1, then the denominator is positive, and overall this critical threshold is positive. So if this is positive, this means that cooperation is favored anytime the benefit cost threshold exceeds this quantity here, exceeds this critical. Anytime the benefit cost ratio exceeds the critical threshold, right? So if the critical threshold is 5, then you need a 5-fold benefit relative to the cost. Now you might think that denominator looks like it should always be positive, right? Because T3 looks like it should be greater than T1. That's actually not necessarily the case. So it could be the case that T3 is less than T1. How might that be? Well, think of a complete graph with no self-loops. If you take 1 step there, then you're definitely at a different vertex from where you started. But if you take 3 steps, you may return to your starting vertex. So in that case, T3 would be less than T1 because of the possibility of returning to your starting point. If that occurs, then your benefit cost threshold is negative. In that case, cooperation cannot be favored at all in the donation game, but there's a possibility that spite could be favored. Spite, remember, means that B is negative, so you're paying a cost to harm another individual.
So if Zuckerberg succeeds, then basically we aren't going to cooperate.
One of the messages here is that complete graphs are not good for cooperation. And I actually believe that to be the case. I don't think we should all be equally connected to everyone else on the planet. It seems like not a great idea. Yeah, so this leads to the conclusion that complete graphs are not favorable for cooperation and, in fact, can promote the evolution of spiteful behavior. It's also possible for T3 to be equal to T1. I'll give an example of this later. In that case, we have an undefined or infinite benefit cost threshold, and neither cooperation nor spite are favored. All right, so these are kind of three categories that we can place graphs in. So now we have a condition, and we can evaluate this threshold for any given graph in polynomial time. It amounts to solving just a system of n-squared linear equations. Applying this result, we'll first look at small graphs. For all the graphs of size 4, there aren't very many of them. We get only one that has a positive benefit cost threshold. So if you're on the line graph, then you need a 4-fold benefit relative to your cost for cooperation to be favored. These graphs here don't favor cooperation or spite. These graphs down here favor spiteful behavior. For size 5, we get some more graphs that are kind of reasonable in their effect on cooperation. Well, still not very many of them, right? So it still seems like for these small graphs, there's a relatively small percentage that have benefit cost thresholds that are positive, but low enough to be reasonable. So these ones up here have a benefit cost threshold greater than 30, which is, kind of unrealistic to achieve, a 30-fold benefit. Top is infinite, bottom is negative in spiteful behavior. And then here's the graphs of size 6. We can kind of see some common themes start to emerge. So the ones that are best for cooperation are more sparse, generally. The ones that favor spite are more dense. For these small graphs, the path is actually the one that favors cooperation most, although that turns out to actually not be the case for larger graphs. Okay, so those are small graphs. We then did a lot of kind of random experiments to figure out what's the overall picture here. If we're kind of looking at any random given graph, what should we expect? So these are 1.3 million random graphs done by my collaborators, because I'm not so great at these numeric things. Different random graph models, including Erdős-Rényi, Small World, Balbashi, Albert, etc. The sizes here range from 50 to 100. We also did experiments with larger graph sizes. For all the ones we looked at here, the critical threshold was either greater than k or negative, which implies that the condition B over C greater than k bar, average degree, is what I mean by that. For all these, this condition was necessary but not sufficient. Okay, so these are some random explorations. We can also look at kind of an engineering question of how would we design graphs that promote cooperation. One recipe is to emphasize pairwise ties between individuals. So we were able to show that if every individual has one neighbor of strong edge weight, then as that edge weight gets larger and larger, the critical threshold approaches 1. 1 is the best possible value attainable. If you have a critical threshold of 1, that just means cooperation is favored whenever the benefit exceeds the cost. So kind of whenever there's a net benefit to society, then cooperation is always favored. Another question we can ask is, if we're given graphs that don't favor cooperation, can we improve them? Yes?
Do you think that there's... Yeah, so human society actually has something of a model like that. Do you think that's coincidence?
Do I think it's, I think it's fortunate. I'm not sure. You know,
I'm not making value judgments about the model. I'm just curious if you've reflected on pairwise bonding as
you know, I think pairwise bonding is a good thing. Whether it was specifically designed to, you know, whether it kind of evolved, whether our social structure evolved to promote cooperation, you know, in terms of these kinds of mechanisms, that's an interesting question. I mean, certainly there's other reasons besides this why pairwise bonding has evolved. So I wouldn't claim that this is the most salient explanation, but I do think it's fortunate to have pairwise bonding. All right. So what if we start with a structure that's not so good for cooperation? So here I've drawn two stars, but let's think of each of them separately. These have a undefined benefit cost threshold. And it's actually very easy to see why. Remember the denominator of this threshold is T3 minus T1. So we're comparing 3-step walks to 1-step walks. Well, if you're on the star, a 3-step walk is exactly the same as a 1-step walk. Right? So the denominator is automatically 0. So these don't promote cooperation or spite. But it turns out if we join them together, we actually get a pretty good benefit cost threshold. So this is a result that's in the limit of a large number of leaves. We have the exact result for all n, but it's rather cumbersome. So if you join the two large stars by their hubs, then you get a very nice, you know, reasonably achievable benefit cost ratio. We can also join them in different ways, such as leaf to leaf. That also leads to a reasonable result. We could start joining the leaves together. So we could call this a ceiling fan structure. It has a benefit cost threshold of 8. Or we could join kind of all leaves to their two neighbors, and then we get this interesting quadratic root that's around 7.7. One structure that turns out to be really interestingly quite favorable for cooperation is we took a large number of stars where each star has a large number of leaves. In fact, we kind of first take the limit of a large number of leaves and then take the limit of a large number of stars. Every star is connected to every other one by their hubs. And kind of in the limit of that, we get a benefit cost threshold of 3/2, which is quite good. In fact, it's less than the average degree in that limit. So this is the first example that we found where the benefit cost threshold is less than the average degree. Yes?
So we're interpreting pain A, and it seems to me that in pain A, the fixation probability should just always be 0.
Yeah, so, right. That's for each graph separately, right? So, yeah. So certainly fixation doesn't happen on disconnected graphs. But we've just drawn the two of them together because we want to eventually link them up. But think of them as two separate things.
So for F, a complete graph of countries, each of which is a dictatorship?
So I don't know if a star is a dictatorship. It's just highly asymmetric. But one common theme that we've found is that kind of having communities, kind of cohesive communities that are then linked together can be helpful for cooperation. Yeah. All right, so we have like each of these functions has its own community. The fact that they're stars isn't actually that important. So you can do something similar with complete graphs where then you pick one individual from from each like click and link them together. And that also supports cooperation. I don't remember the number, but it's another reasonable number.
Cool.
Yeah.
That's kind of
It
cool.
is. Okay. So these are the end of the kind of basic results. We can extend in various ways. So we can look at games besides this donation game. In this case, there's something called the structure coefficient theorem, which says that basically, if I have this 2x2 pairwise game, the condition for success always takes this form, with a certain coefficient sigma that's attached to the two diagonal entries here. And that's very nice because I can study just one game to find this value of sigma, and then that gives me the condition for all games. Right? So using our results on the donation game and applying this structure coefficient theorem, we can obtain this condition where sigma is equal to this. So that's a quite powerful result. We can also amend the model by looking at different update rules. We can look at accumulated payoffs. That means you just add the payoff from each neighbor instead of averaging. We can suppose that maybe interaction happens on one graph and replacement happens on a different graph. That's also a reasonable extension. And we can also look at non-zero mutation. So in the paper, we have results for all these extensions. Basically, they all come down to coalescence times, different expressions involving coalescence times. For mutation, instead of coalescence times, we need something called identity by descent probabilities, which is a closely related concept. So in conclusion, we have identified a numerical and not too difficult to calculate condition for any game strategy to be favored on any undirected graph, as long as we assume weak selection. Right? This is a rather strong assumption, and it's hard to make much progress beyond this. And we can compute this in polynomial time. And we find that cooperation is most strongly promoted when there are close pairwise ties among individuals. So that is nice to know. Oh, I guess I had open questions. So we have a way of computing this threshold, but we are still kind of trying to develop an intuitive understanding of it, especially for heterogeneous graphs. So we want to know how it relates to, for example, the degree statistics beyond the average degree, maybe the spectral properties of the graph. There's another update rule that we're not even sure whether it can promote cooperation for any graph. It's still under investigation. And there's a few new conjectures that we came up with regarding random walking meeting times on graphs. And thank you. These are my collaborators.